All right, in today's lesson, we're going to be talking about the compound angle formula. This is one of two formulas that we can use to help evaluate our trigonometric ratios. Where this comes from is the concept of compound angles. And compound angles essentially are trigonometric expressions that depend on one or more angle. And you'll sort of see how that comes to play. But essentially, what we're trying to do is we're trying to manipulate trigonometric equations so that we are able to use our special triangles in order to get exact answers. Remember, very often we're looking for the most precise answer, and if we're able to express it as one of the special triangles, then that is our goal. For this course in advanced functions, you do not need to know how to derive the compound angle formula. You just need to know how to apply it and how to use it. However, if you're curious and you want to see what or how they come about, then check out page 228 to 229 in the textbook. Okay, so there's two sets of formulas that we need to sort of memorize. That's the expectation here. We have our cosine formulas and we have our sine formulas. Fortunately, there's a lot of repetition in how the formulas are written, and so they are pretty easy to memorize. In both sets of formulas, obviously there's two angles that we're dealing with, an A and a B. And then cosine formulas use cosine, sine formulas use sine. And how are they broken up? So in our first formula here, our first couple of formulas, the cosine ones, they both start with a cos A times cos B. And then there is a symbol, plus or a minus, and then it moves into sine A, sine B. Now if our formula has a minus sign in it, as in cosine of one angle minus the other, then my formula will have a plus. It's going to be the opposite. Just like if I have a cosine A plus B, then the thing in the middle there is going to be a minus, okay? So we can see that they have opposite signs. And then coses stick together and sines stick together. With our sine formulas, you'll notice that the terms are a little bit different. In this case, we are still doing an A and a B, but we have a sine times a cos. So sine A cos B, and then cos A sine B. So it's opposite. In the cosine formulas, the coses stuck together. In the sine formulas, they don't. They're split up. However, the signs within the question and within the formula are the same. Just a little sort of trick, things to notice to help you memorize these. Of course, reference them until you have them memorized. They are pretty easy to memorize. And then just as a reminder, we do have some special triangles here that we need to be dealing with. Remember, the goal of our composite angle formulas is to use our special triangles in order to solve. So we're just going to add them here so that we've got them as good reference. Awesome. Okay, so let's do one example really slowly, and you'll get the feel for what's going on here, okay? In our first example, we're asked to evaluate cosine of 7 pi over 12. And so what we need to determine is what two special triangle angles can either be added or subtracted in order to get to 7 pi by 12. Well, let's just think for a second here. In our special triangles, we basically have three angles. There's pi by 4, pi by 3, and pi by 6. They would all have a common denominator of 12. Pi by 4 would be 3 pi over 12. Pi over 3 would be 4 pi over 12. And pi over 6 would be 2 pi over 12. So these building blocks might be a little bit easier to visualize. So again, back to my question. which two angles can be added or subtracted in order to get 7 pi by 12? Well, let's just take a look here. If I take a 3 pi by 12 and a 4 pi by 12, that gives me 7. And so the two angles that I'm adding, in this case adding, are going to be pi over 4 and pi over 3. I'm just going to write that out here. 7 pi by 12 is 3 pi by 12 plus 4 pi by 12, which is pi over 4 plus pi over 3. We are adding, and therefore we are going to use the addition formula. We also have a cosine, and so we are using our cosine addition formula. Okay? Remember the cosines, the coses stuck together, and the sines stuck together, and then the sign in between the two of them was opposite. So in this case, it would be subtraction. And what are the two angles that we are dealing with? Well, we just found them. Pi over 4 is going to be angle A, and pi over 3 is going to be angle B. And so I'm going to substitute that into my formula now. It'll be cosine of pi over 4 times cosine of pi over 3 minus sine of pi over 4 times sine of pi over 3. Okay, let's go back and reference our special triangles now in order to be able to solve. I'm going to zoom right out. Cosine of pi over 4 is going to be adjacent over hypotenuse, so that is going to be 1 over root 2. Cosine of pi over 3 is going to be 1 over 2 minus sine of pi over 4 is going to be 1 over root 2. And sine of pi over 3 will be root 3 over 2. Cool. Now we can simplify. Let's actually do this multiplication. My first term will be 1 over 2 root 2, and my second term will be root 3 over 2 root 2. And I'm going to just combine those terms because they have a common denominator. 1 take away root 3 over 2 root 2. Okay, that is our exact answer. That is our most precise answer. And we're able to find this thanks to the composite angle formulas. Okay, let's do a couple more. Determine the exact value of the following. Okay, cosine of 5 pi over 12. So which two special angles are going to get me to 5 pi over 12? Well, it looks like I can add 3 pi over 12 and 2 pi over 12, which is pi over 4 and pi over 6. I'm just going to write that down here off to the side. 5 pi over 12 is equal to pi over 4 plus pi over 6. Those are my A and my B. I am dealing with a addition cosine formula. And so we write it out. Cosine of A plus B will be cos A cos B minus sine A sine B. And let's substitute. My question was 5 pi over 12, and I substitute in A for pi over 4, and then pi over 6 for B. Cool. Now let's go ahead and simplify. Cosine of pi over 4, we go back to our special triangles. Adjacent over hypotenuse, so is 1 over root 2. Cosine of pi over 6, I go back, root 3 over 2. Sine of pi over 4 is also 1 over root 2. And sine of pi over 6 will be 1 over 2. Okay, we can multiply and then we can simplify. Our first term will be root 3 over 2, and our second term will be root 3 over 2 root 2. And our second term will be 1 over 2 root 2, which we can combine into root 3 minus 1 over 2 root 2. Awesome. Okay, let's do another one. Sine of pi by 12. Okay, which two special triangle angles are going to get me to there? Well, we can take a look if we need. It looks like if I have a 4 pi by 12, take away a 3 pi by 12, that would work. Just like 3 pi by 12, take away 2 pi by 12 would also work. Doesn't really matter. Let's do pi by 3 and pi by 4. So I've got my A and my B. We are dealing with a subtraction here, but this time it's the sine formula. So remember that the sine formula with the subtraction, our sines and our cos's stayed together. So I had sine A, cos B, and then cos A, sine B. Move this over just a bit. There we go. And the sine in the middle was the same in our sine formulas. Okay, we can substitute in. I am going to have sine of pi over 3, cosine of pi over 4, minus cosine of pi over 3 times sine of pi over 4. Okay, let's go to our special triangles here. Sine of pi over 3 will be root 3 over 2. Cosine of pi over 4 is 1 over root 2. Cosine of pi over 3 is going to be 1 over 2. And sine of pi over 4 is going to be 1 over root 2. And you can always reference your special triangles when you're finding that. It's a-okay. Okay, let's go ahead and do our multiplication. Our first term will be root 3 over 2 root 2. Take away 1 over 2 root 2. And we can combine these terms because they have a common denominator. Root 3 minus 1 over 2 root 2. Awesome. Okay, let's look at a little more of a challenging question here. Similar to something that you might find in the textbook practice. So we are given some information in advance. We know that sine of our x is 4 over 5. There's a second variable as well, cosine of y is our second variable, is negative 5 over 13. And in this case, both x and y lie in the range pi over 2 to pi. Well, what does that even mean? They lie in this range. Think about our Cartesian grid. Up here is pi over 2, and if we keep going, this is pi. So what the question is telling me is that they lie in my Q2. First thing we're being asked to find is the exact value for sine of y and cosine of x. How on earth are we going to find that? Well, my suggestion is let's just draw it out, okay? Let's do sine first. Or let's do our angle x. So we know that angle x lies in quadrant 2, so I'm just going to draw this. And we know that sine of my angle x is 4 over 5, and sine is opposite over hypotenuse. So if my angle x is in here, the opposite of my angle x is 4, and my hypotenuse is 5. Well, can I use this then to, just putting an x there, to figure out what the last triangle, the last side of the triangle is? Yeah, I absolutely could. I could use our Pythagorean theorem. We have a right angle triangle. 5 squared will be equal to 4 squared plus, let's do b squared. 25 is 16 plus b squared. I subtract 16 from both sides and get 9. So 3 is my missing side. And in this case, it's actually going to be -3 because it is on the negative x-axis. Okay. Now that I know all 3 sides of my triangle, can I find cosine of x? Absolutely. Cosine of x is adjacent over hypotenuse. My adjacent side to my x is -3. And my hypotenuse hasn't changed at 5. That is my exact value for cosine of x. We can use the same steps in order to find y, or in this case, sine of y. We draw a quick grid. We know that it's going to be over here. And in this case, so for our y value, cosine of y, we were told the adjacent is 5. So this is y. We finish our triangle. Our adjacent is 5. Our hypotenuse is 13, and there's a negative sign. And where is the negative sign going to go? Well, it's not going to go on the 13 because hypotenuses are always positive. It is going to go on the 5 though, because the 5 is along our negative x-axis. We can once again use the Pythagorean theorem to figure out our missing side length of this triangle. 13 squared will be equal to -5 squared plus b. 169, then will be 25 plus b, or 144 is equal to b squared. So 12 is b. And it's going to be positive, it's going to remain positive because it is in the positive y-axis. Okay, so let's find sine of y. Sine of y will be opposite, so 12 over hypotenuse 13. So just to recap here, because this is only the first part of this question, given these ratios, we were able to construct a triangle knowing as well which quadrant it was in, and then we were able to determine other trigonometric ratios for it, which is very useful because, you know, we're going to do something else with it, okay? Question B is now asking us to find the exact value of cosine of x plus y. Let's start by writing out our formula. We have a cosine formula here, and so we remember that the cosines stick together and the sines stick together. And the sign in the middle is the opposite of the one in the brackets. Okay, well, we now know a whole bunch of stuff. We know cosine of x. We just found it in the last question. Cosine of x is -3 over 5. Cosine of y we were given originally. It's -5 over 13. Sick. Sine of x, we were originally given in our question. It's 4 over 5. And we just found sine of y. Right there, 12 over 13. Sweet. So now we can actually go through and multiply these things and then add them together. In my first term, the negatives will cancel out. I'll multiply my numerators together to get 15. My denominators together, 5 times 13 is 65. You may have been able to jump to, well, I've got a 5 in my denominator, a 5 in my numerator. I'm not doing that. I'm not simplifying out here because I recognize that I will need a common denominator eventually, and 5 times 13 will be the same common denominator as 5 times 13 over here. My second term, 4 times 12 will be 48, and my denominator once again will be 65. So I can go 15 minus 48 is negative 33, all over 65. Cool. Okay, and then last but not least, let's find the exact value of cosine of y minus x. So I'm going to use my cosine formula here once again. Cosines stick together. The sign is opposite. Let's fill in some information. Cosine of y was negative 5 over 13. Cosine of x is negative 3 over 5 plus sine of y was 12 over 13. Sine of x was 4 over 5. I just got those from referencing our previous question. Okay, let's multiply. We're going to get the same fractions. 15 over 65, 48 over 65. This time, it's just a plus sign in between the two. All right, and 15 plus 48 will be 63 over 65. Okay, and that's the gist of your compound angle formulas. Okay, it's really just a matter of sort of plugging numbers in once you can figure them out. Really, truly, the hardest part in all of this is figuring out which two of our special angles can be combined in order to get our exact ratio. Alrighty, and that's it. Well done, everybody.